Let me start again. Hey, what's up guys? Today we're gonna see how a MOSFET works, the basic operation of a MOSFET. Now, over here I'm assuming you already know what a MOSFET is. You probably enrolled in some electronics course which you are maybe finding it to be very difficult, moderately difficult, but it's definitely not easy, but So, today we're gonna be studying the basic operation of a metal oxide semiconductor field effect transistor, right? And how it works, right? So, for those of you who don't want to read the textbook, this is the simplified diagram of a MOSFET, right? This is your body, where you have, now I'm talking about an NMOS over here. Let me mention that since the beginning. So, I'm talking about an NMOS over here. The structure of NMOS looks like this. You have a P-type body. This is your drain, this is source. Okay, this shaded region over here is your oxide layer of SiO2, and on top of which is your metal terminal, right, where you input some positive or negative voltage, VDD, or I don't know, maybe alright, fine, let's name it VDD. Alright, fine. Now the working of the MOS is like this. Alright, now you have P, this region is basically a P region, right? You have holes over here. So if you want to conduct the current between your source, hold on, give me a moment. Yeah, so if you want to conduct a current between your source and your drain regions, you can do so by, through holes, but then the current will not transfer because the only two diodes, right? There are two pairs of diodes over here. One is this P and N diode, and another is this P and N diode. So the current transfer will occur only between these two diodes and junctions. And what we actually want over here is current transfer between the source and the drain, right? Now, so how do we do that? This is where the MOS comes in, alright? Now, the MOS conducts current through an electron channel. Let me repeat that. It conducts through an electron channel. Now, you might be asking over here that since the body is a P substrate region, and if the current has to flow from source to drain, it must do so through holes. So where do the electrons come in? Well, this is what is special about the MOSFET. What happens is, when you apply, this is the metal, fine, so when you apply a positive voltage VDD over here, okay, the holes over here will get repelled by this and will start moving downward, fine, because of the field. Obviously you have a positive field over here, right? So these these holes, they start moving downwards, because they get repelled by the field, right? Let me rub that quickly. Don't buy Galaxy, don't, you'll regret it. Ah, come on. Yeah, you know what I mean, right? Okay. So what happens is, these holes, they start moving downwards. Give me a second. Right, now what's left is, see, the basic structure of a P-type semiconductor is you have an ion. Hold on, give me a second. You have an acceptor ion, right, of an element like nitrogen or phosphorus, etc., right? And these have 3 electrons. They want a 4th one, so they take an extra electron from the semiconductor and leave a hole in place, right? So these are basically negative ions. So when the holes move in this direction, they essentially leave negative ions over here, right? Okay, fine, but still this doesn't answer any question. I mean, these ions are practically immovable. They cannot move. So where are the electrons that I talked about? How the current is going to be conducted? Alright, now we're coming to that. So what happens is that as you further increase this VDD, what happens is, now instead of the holes getting repelled, right, there are ions here, okay, which have an extra electron tied to them. These ions, they have this extra electron tied to them. Now the field at some point of time increases so much that these electrons are attracted towards the oxide layer, right? But they cannot travel through the oxide layer. Why is that? Because oxides are insulators. They have very high resistivity, because of which they cannot conduct any current. So these electrons, they they get attracted here, okay, and they just stop there, okay. So this is a channel. Now when you apply a positive voltage here and a negative voltage here, okay, electrons will enter through here, okay, will travel through this channel and will exit over here. So essentially you have formed, and if you connect these positive and negative terminals, you have completed a circuit. This is the channel that I was talking about, and this is how a MOSFET works. So what happens is, basically, is when you increase VDD enough, okay, to a particular voltage value, let's call that value VTH. You'll understand why I'm calling it VTH right now, right? So what happens is, the positive voltage, this field is so much that it starts attracting the electrons towards the oxide layer, okay, which forms a very thin channel, right? I'm talking about micrometers, I'm talking about nanometers here, right? So it is so thin, right? This channel is what is makes the MOS capable of conducting any current, right? Now consider this. Fine, you increase voltage VDD over here, and the number of electrons increases, which means that to conduct a particular current, there are more electrons available, right? So if there are more electrons available, that means the resistance of this channel decreases. So essentially, a MOS is a voltage controlled resistance. Voltage controlled resistance. Why is that? Because when you increase VDD, the number of electrons increases, thereby making the MOS channel more conducting, or thereby decreasing the resistivity of the MOS channel, right? So here is how the MOSFET works, and I hope you understand what I said, although I may not have been a little as fluent as I had wanted myself to be, but still I think I gave satisfactory explanation. Anyway, have a good time studying electronics and don't lose faith. Adios.